Hello, today we'll be talking about simple harmonic motion. Another way to say that would be, or describe it as oscillatory motion. Some functions that you may know which help explain this are the sinusoidal functions, such as sine of theta, cosine of theta, and tangent of theta. What these functions do, and what oscillatory functions have as a whole, is they model functions that repeat themselves over time. For instance, if you were to graph sine of theta, you'd end up with this. Over time, you have a repeating motion. Whereas at this point 0, at this point 2 pi, at this point 4 pi, so on and so forth for infinity, you will have a repeating function. And that's one of the main concepts of simple harmonic motion, with an example commonly used being one of a mass on a spring. As if you apply a force opposed to motion, you can end up with the spring going back and forth, and you have what's called simple harmonic motion. So let's start off with a problem like that and introduce an equation. With this equation and this problem, we're going to start off with a spring with a mass of 3/4 of a kilogram and a spring constant of 300 newtons per meter. The spring constant is it's a constant of the spring, which that times the value of x will give you the value of force. For instance, if you were to have a spring halted from the ceiling holding onto a block and it was not under acceleration, you'd have one force of gravity heading downwards, and then this force that we call F is equal to kx acting in the other direction. Then you get some value mg is equal to kx, and you can solve for k in newtons per meter that way. However, in this case, we're going to start out with an equation. What we want to find out is the period. For instance, in this case, we want to find out how long it takes for the cycle to repeat itself. As we know in the function sine of theta, we get 2 pi over 1, so it repeats itself every 2 pi because it's 1 times theta. In this case, we're going to use the equation that the period of this is equal to 2 pi times the square root of the mass divided by the spring constant. That's something that's derived through differential equations. I won't be going through how we derive it, however, it is one equation that you need to know pertaining to these types of problems. As we can tell, we'll be able to plug in some values. 2 pi times the square root of k over m over k, 0.75 over 300. What we will end up here is the period, or how long it takes to repeat itself, and you will get here 0.314, so pi over 10. So 0.314 is how 3.14 seconds how long it takes to repeat itself. Another thing you'll want to know is the frequency. We know is that 2 pi f is equal to t. Whereas the period is how long it takes to repeat itself, the frequency is how many times it takes place in a second. So if something has a frequency of 60 revolutions per second, that's an example of that. We know f is equal to 2 pi, is t over 2 pi. We can solve it that way. Let's go on to another example of a more conceptual example. A conceptual example of this, and as we know with oscillatory motions, another way to describe it is as wave functions. Two examples that come to mind are one of bats using echolocation. They'll use sound waves, bouncing off objects, coming back in order to distinguish where they are using sound. As well as in the ocean, there's things called rogue waves, or just waves in general, where you have sinusoidal waves, or in some cases rogue waves, which are much larger, which you can calculate different things based off of them. Now, the primary function we use to help distinguish these, the waveform of function, as you can call it, is that describing the displacement, so x of t is equal to a, which is the amplitude, times cosine of omega t plus phi. Of course, x is the displacement of t is sometime t. A is called the amplitude. As you know, whenever you graph sine and cosine, these peaks and valleys, as we call them, here and here, are equal. If you if you were to plot this, this is sine. If you were to plot cosine, that would start up here and move like this. The peaks and the troughs will be marked as 1 and -1 if it's that. However, when you change the amplitude, you change those peaks and troughs. If I correctly do cosine this time, let's say that the amplitude is 2. This becomes 2 and this becomes -2. You can tell by the multiplication here that that would be the case. However, if you were told to find the amplitude given a function, say 0.75 cosine of omega t, the amplitude is 0.75. Now let's get inside of cosine. Within the cosine, we have omega t plus phi. Now omega, that is what helps you find the period. For instance, we know that the period of just cosine of t is 2 pi over 1. However, the period as stated, you can find it as 2 pi over that constant omega. And that'll be what helps you find how long it takes for the function to repeat itself, where omega is a multiplier. Finally, phi is the phase angle, which can offset it if that's required for the function. However, if that value is pi over 2, then you could change it using laws of sine and cosine and change it into sine, as that's how you're able to offset the functions. One important thing to know about simple oscillatory motion is that as long as there's no variable times that cosine or sine, you're able to shift, I guess. You can shift the function as long as you want, and you will end up with, this isn't a perfect drawing, but you'll end up with the same values for all real numbers. And the functions don't approach any distinct number as it goes to infinity or negative infinity, respectively, as they are oscillatory. Thank you for watching. This has been one on waves and oscillatory motion.